interesting.
Okay.
Please.
Yeah, so first of all, so I'm sorry that my lectures are a little bit crammed. The reason actually being is that I'm currently on holiday, and 2 days was the most that my family gave me to escape from holidays. So unfortunately, after this, I have to rush to the airport. I'll be here until 12:50, so I'm happy to chat until then. Okay, so if you have questions afterwards, we can chat until 12:50. All right, and in fact, so this last lecture I'm expecting to be a little bit shorter. I only have 20-something slides. So what I thought, there's a chance, who knows, there's a chance I will finish 10 minutes earlier or so. And then what I thought we could do is we could have some kind of Q&A style. I saw that David was, for example, doing this for an entire hour. But so if already now you can think of questions on anything in cosmology or anything that was covered in these 3 lectures, then maybe we have time at the end. Okay? Okay. So now I want to talk about well, let me first remind you what we did so far. So far we have described the evolution of fluctuations in the hot Big Bang, in the primordial plasma, and then we discussed how these primordial fluctuations evolve in time. So at first they evolve as sound waves in the plasma, and we see snapshots of those sound waves in the cosmic microwave background power spectrum. And then at later times, those small fluctuations, which are fluctuations in the density in the early universe, grow under the gravitational influence and produce galaxies and stars and all the structures that we see around us. Okay? So that's, I would say, a very well understood kind of standard history of cosmology that was developed in the last kind of 100 years or so. And so now we want to get even more ambitious and try to explain what created these initial fluctuations. Remember, there's actually the power spectrum was evolving in stages. It started very featureless, perfect, just a horizontal line with nearly scale invariant fluctuations, equal power on all scales. Then the sound waves were transforming this into this kind of oscillating pattern with peaks and troughs. And then finally, the dark matter fluctuations kind of was getting this kind of smooth shape with kind of 2 different scalings and a peak in the middle. So there's 3 different power spectrums at different moments in time, and we have a story to tell how these things get kind of evolved into each other. But now we want to step back and actually go to even earlier times and ask what created this scale invariant spectrum that we have to use as our initial condition. Is there a dynamical theory of those initial conditions? Okay? And so at first, I want to show you just an important clue for what that physics could be. And so the important clue is the fact that when you look at this power spectrum on the CMB, it has fluctuations on even the very largest scales, or correlations on even the very largest scales. Yeah, and so here I'm showing you again on the x-axis angular separation, and I've now indicated kind of the different angles here. So we start with 90-degree angle, which is the largest fluctuations we can measure, as I said last time. And then as you move towards the right side of the plot, we're measuring smaller and smaller features, smaller and smaller 2-point correlations, and smaller angular separations. But within the Big Bang model, you can actually compute, just given the finite age of the universe at the time when the CMB was released, what's the maximal size of angular separation of the physical particle horizon at the time when the CMB was created. And that calculation will give you that it's 2 degrees on the sky. Yeah? And so, but nevertheless, we see things being correlated over larger than 2 degrees on the sky. Okay? So in the standard Big Bang, this is impossible. This manifestly violates causality. So let me just explain this with this picture here. Okay? So what I'm showing you here is the Earth kind of at the center. There's a spherical region around the Earth that's created by the surface of last scattering. So there's a moment in time that creates a surface around us when the first light was emitted. And so that's the surface of the CMB. It's a 2-dimensional surface around us. And so we were projecting this onto a map, but what we're really seeing is this spherical surface around us. Yes, there was a question.
Let's imagine that in the beginnings of the Big Bang, after that, after inflation, after CMB, in the CMB we have an electron and positron.
Yeah.
They will annihilate into photon, and after that we have detected photon in the now. And what's the difference between how can we differ coming from the early universe and other sources like sun or
Okay, good.
black holes?
let me repeat the question maybe for everybody. So I think you're talking about, so at very early times, this was happening at 10 to the minus 19 seconds, the annihilation of matter and antimatter into high energy photons. But then actually the universe still goes through a phase of thermal equilibrium afterwards. Yeah? So these photons will mix with the matter into the primordial plasma and are just characterized by thermal equilibrium with black body distribution functions and temperature. And then, so that's why it's also so hard to test baryon asymmetry as a theory, because things are washed out by thermal equilibrium. And then the CMB is relieved afterwards. So you can't distinguish those photons. Those are the same photons, yeah, that was coming from matter, antimatter annihilation, but there's no trace of their origin. Those photons were coming into thermal equilibrium, then they're being released when the plasma becomes transparent to light. And so, yeah, there's just, they are the same photons, but they don't have a label attached to them that tells us about the matter-antimatter annihilation. Okay? Okay, but let me come back to this picture. So now there's this surface surrounding us, and you can compare, I've also drawn here in red, little circles that indicate the maximal distance that light could have traveled from the time of the Big Bang. Okay? And the Big Bang itself actually is a surface surrounding us that's a little bit larger than the surface of last scattering, okay? Because of the finite age of the universe. And so you see what I've drawn here just schematically is, there's a minimal angle where these two neighboring horizon circles just touch, okay? And so if we were to separate these 2 points just a little bit further, then these two circles would not overlap, okay? And that means they're out of causal contact, yeah? And so in fact, you can take the entire surface of last scattering and you can separate it in 10 to the 4 regions of a size given by the maximal size that light could have propagated since the hot Big Bang. And the puzzle is why, first of all, there's two puzzles. The first puzzle is why is the temperature almost the same across the entire sky, while usually we expect thermal equilibrium to operate on scales smaller than the particle horizon. Yeah, so it would be totally reasonable in the standard hot Big Bang that there were fluctuations in one of those red circles that are much larger than in the other red circle. So there's a temperature of 2 degrees in one circle and 5 degrees in another circle and so forth. Okay, that's the first puzzle. And the second puzzle is, so why is it so homogeneous? But then even if you have some kind of deep symmetry reason for why things are homogeneous, maybe it's the most natural thing to have to be smooth, you then, on top of those smooth temperature, there's also fluctuations, and the fluctuations themselves are correlated. They're not random, and they're correlated over distances that are separated by more than the light travel time since the hot Big Bang. Okay? So there's two types of, these are called the horizon problem. There's two types of the problem. Why is it so smooth, and why, despite not being exactly smooth, why is it correlated over distances that span the entire sky? Okay? So it's worth thinking a little bit about this picture here because it explains the entire issue. Okay, this is another version of the picture where I've now shown you the past light cone from our vantage point. Yeah. So basically, the picture that I showed you just on the previous slide was like a top-down view of this, where this past light cone is intersecting the moment of recombination and creates a circle. But I can also, of course, look at it as a function of time, where the time axis here is on the y-axis, and then space across. And so there's another way of seeing that the future light cones of any given 2 points at the hot Big Bang are not overlapping if the points are separated by too large of a distance. Okay. So what this really is telling us, before doing any theory, any speculation about inflation and so forth, there's just an observational fact that we have learned some 20 to 30 years ago, is that the hot Big Bang was not the beginning of time. That whatever created these correlations must have operated. It could not have been some magical mechanism within the hot thermal phase of the universe that creates these large-scale correlations. That violates causality. If you want to respect causality, you have to extend time before the moment when the universe first became a thermal plasma. So something was before. That's a fact, okay? What's not a fact is what exactly that thing is that created these correlations, okay? So the most likely explanation, for reasons that I will also explain, is that there was a period of extremely rapid exponential expansion, in fact, where space itself was expanding at a superluminal rate. Yeah? So space itself was expanding faster than the speed of light. Okay? This doesn't violate relativity, because relativity only tells you that objects can't move through space faster than the speed of light, but the space itself can stretch at a rate that's faster than the speed of light. And so by doing that, you can take a tiny patch of space. That patch of space has reached thermal equilibrium just causally by heat flow from one region to the next. And then you take that region of space and you expand it by an enormous amount. In fact, this is one way of visualizing the amount of expansion. So first of all, this period lasted for less than 10 to the minus 32 seconds, we think. So in a blink of we can't even visualize how short that is. Okay? And the universe doubled in size at least 80 times in that period. So what this means is take a region of space the size of this fly. If you double this in size 80 times, you will generate a region of space the size of our entire galaxy. Okay? And our entire galaxy is hundreds of thousands of light years across. And a light year is many, many kilometers and so on. So you can convert these things to each other. And you can do other crazy, for example, the entire observable universe came from the region of space the size of my fist. Okay? So everything that we see around us kind of was inflated out of a region the size of my fist. Okay? Okay, but this is apparently what we have to do if we want to kind of maintain causal connectedness between different regions of space. Okay? Any questions about this? It's just mind-blowing. Okay? The really mind-blowing thing is that we can test this experimentally, that we can actually see evidence for this kind of crazy sounding proposal. Now, so in order, we have already seen the mechanism that can do this. So notice that I mentioned here that the scale, I showed here that the scale factor increases at an exponential rate, e to the ht. And we have seen already before, we in fact derived it even, for dark energy, that the scale factor goes as e to the ht if the energy density of space is constant. Okay? And so inflation is just like that, but at higher energies. So you need an energy density like a cosmological constant, but now this cosmological constant can be a large value. So it's actually easier to explain inflation than dark energy, because it could literally be maybe some vacuum energy effect with less cancellation than it's needed in order to explain dark energy. Yeah? So what we'll need is a nearly constant energy density. Yeah? One difference to dark energy is that this energy density cannot be exactly constant because inflation needs to end. Dark energy doesn't need to end, in principle. It could just stay constant until the end of time. Okay? But inflation needs to end because we need to transition to the hot Big Bang, and we need to kind of create the late universe that we see around us. So it is approximately constant, but it cannot be exactly constant. And therefore, usually we describe this in terms of some kind of potential that's parameterized by a scalar field that has kind of a very shallow part where it acts like an effective cosmological constant. But then at some point it turns over and the field starts rolling, and when it starts rolling, then inflation will stop. And by coupling these fields to the standard model, you can then populate the degrees of freedom of the standard model and create the hot Big Bang. Okay, that's the basic picture. Okay, yeah.
Could this thing, the energy density, could it be the Higgs field?
Mm-hmm. Of course, this would be super attractive because we need a scalar degree of freedom, otherwise things become anisotropic. So the Higgs would, of course, it would be very economical to have just one scalar field, the only scalar field fundamentally that we discovered in nature, also playing the role of the inflaton at early times. If you can actually do the exercise. It's actually a nice exercise once you learn about the slow roll equations of inflation, to take the Higgs potential and ask, is there anywhere on the Higgs potential where you could inflate? And the answer is no. Just taking the standard Higgs potential, just because the parameters of the Higgs potential are kind of too well constrained to allow for inflation. Now, of course, this is also, by doing this exercise with fixed parameters of the Higgs potential, you of course making the strong assumption that there's no running of those parameters going to extremely high energies. So maybe those parameters will change as you go to high energies, and people also here at CERN, I think, or in Lausanne, have played with this idea of coupling the Higgs non-minimally to kind of the Ricci scalar of Einstein gravity that would then change the Higgs potential when you go to very large VEVs or high energies. And so it's possible, but then it has very unnatural parameters. So unfortunately, this coupling to the Ricci scalar comes with a dimensionless number that's chosen to be 10 to the minus 5 or something like that. And so that's a small number that we don't like very much. And then there's a question about radiative stability of the potential and all these kind of fine-tunings. But with a lot of fine-tuning, you could maybe make the Higgs with an extra coupling to gravity that's not the standard one, be the inflaton. Yeah. Okay. Any other questions? Okay, so I already mentioned that kind of this kind of effective vacuum energy that's describing the inflationary period has to end or decay. It's a bit like radioactive decay. Yeah, where imagine you have some material that has constant energy density, but then it's unstable and has some rate to decay. And in quantum mechanics, that rate to decay, of course, is probabilistic. So certain regions of space will decay first, and others will decay later. Okay, and so one of those decay, so it produces kind of like a Swiss cheese type structure with holes where the inflationary energy density has decayed and transformed itself into kind of the standard model particles. And we think that one of those decay products is our Big Bang universe. There might be others kind of spatially separated from us, and we can never see them for causal reasons, because the space in between, this gray region is still inflating, okay? So it's traveling at faster than the speed of light. So we cannot see light from these other decayed regions. So there's multiple Big Bangs, basically, and we live in one of them, okay? And so we are a product of one of those decays, and we can only see this single bubble surrounding us. Now, an important feature also is that because of quantum mechanics, that this end of inflation or this decay isn't spatially homogeneous, that there can be these variations because the time of decay can be ever so slightly different at neighboring points. And so that's what we think produces kind of density fluctuations in the late universe, because some reason will keep inflating just a tiny amount of time longer, so they will maintain a higher energy density, while another region nearby will decay first. And once it decays, in the standard model, everything dilutes. And so it will have smaller energy density. And so that creates kind of, out of tiny, tiny quantum fluctuations, kind of large density, large in the grand scheme of things, meaning 10 to the minus 4 over the average. But large relative to the quantum size of those fluctuations. So that's the mechanism. Otherwise, there are quantum fluctuations right now in my hand, no problem, okay? But those quantum fluctuations don't amount to anything. They're just virtual particles that are being created out of the vacuum. They decay, they annihilate again. What's special about inflation is that these fluctuations themselves lead to the switch that tell inflation when and where to end. And then because inflation is such a rapid expansion, it amplifies these fluctuations and creates large gradients in the density. That's the kind of, yeah. Last night I was inspired to write an appendix to actually derive the power spectrum from these fluctuations using only like the quantum mechanics of a harmonic oscillator, okay? And so there's 3 or 4 pages that a little bit more technical than the other appendices that I've written, but hopefully, in principle, I think you have enough physics background to see this, and I actually derived for you the famous result for the 2-point correlation function from inflation using just harmonic oscillator physics. Okay. Okay. Are there any questions about this? No? So I think I will fulfill my promise of finishing early, so then we'll have time for questions. Okay. There's a few things that now I've already mentioned, like the fact that in quantum mechanics, empty space isn't empty, but has these violent fluctuations. This would also be a video, I think, in my keynote. You can just see fluctuating things. These are actually fluctuations in kind of the gluon fields of QCD. And so, of course, these quantum fluctuations, they're real, but usually they have small effects. Real meaning, we wouldn't be able to explain basic features of atomic physics, like the Lamb shift, there's tiny shifts in the energy levels of the hydrogen atom that require kind of these vacuum fluctuations of the vacuum. There's a running of coupling constants that are measured here at LHC that also wouldn't work if the vacuum didn't fluctuate in this sense. So these things are definitely real, but as I said, usually they're not, you have to measure things very precisely in order for these things to be relevant. While during inflation, they get amplified because the fluctuations get stretched. And in fact, the fluctuations induce this switch between a region that inflates and a region that doesn't inflate. And so then this picture that we had before, where we had the initial surface of the hot Big Bang, then we had a surface of when the first photons were released, and we have the formation of galaxies and so forth at later and later time. Inflation now extends this into the past, and it takes vacuum fluctuations and stretches them to enormous scales. Okay? And so those vacuum fluctuations, due to the stretching, become classical density fluctuations and create kind of these initial perturbations. And we also have an explanation why the fluctuations are so featureless and scale invariant. They're scale invariant because inflation is nearly time translation invariant. So the fluctuations are generated on different scales at different moments in time when a fluctuation crosses the horizon. And so inflation takes a scale of a given wavelength and it stretches it by the scale factor. And at some moment, that wavelength will cross the particle horizon and freeze. And at that moment when the fluctuation becomes a large density fluctuation. And this will happen at different moments in time for different wavelengths because, of course, a longer wavelength will cross the horizon first, and a shorter wavelength will cross the horizon later on. But since the conditions during inflation are the same, almost the same, because it's a constant vacuum energy density, it creates the same power for each of these wavelengths. And that's what you're seeing in this plot. Except there's a small tilt, and this small tilt is also understood because the energy density has a tendency to decay in order for inflation to end. And that decay means that shorter wavelength fluctuations will receive a little bit less power than long wavelength fluctuations, which is exactly explaining the right sign of the tilt. Yeah? So here's long wavelength fluctuations on the left. They have slightly more power because they exit the horizon first when the energy density was still a little bit larger. Okay? And then in last lecture, we already discussed that once you have these initial conditions, it's well understood how to take them, evolve them forward in time, and predict the CMB. Right? And we have seen this amazing picture of how this all works. So this red curve has as an input these two parameters that describes the initial conditions, and inflation is a way of explaining where those two parameters come from. Okay. Are there questions about this? Okay. So now, I mean, okay. It's now a bit up to taste how convinced you are by this story, whether you think this proves that inflation really happened. So the scale invariance is rather tantalizing as telling us that there was some phase of time translation invariant, and by definition, that's what inflation is. But it's really also an extraordinary claim, and there's a saying that extraordinary claims require extraordinary evidence. And so for inflation, we don't have extraordinary evidence, I would say. We have good evidence that something like that happened, but not extraordinary. And so it would be nice to find more. And I think the standard should maybe be that we would like to have inflation be on this timeline that I was drawing with the same level of confidence that we were putting BBN there. Yeah? So I'm claiming BBN is a fact. There's no way around it. It will stay a fact until the time we all die. Okay? It's just and after that also. And so the question is, can we put inflation with the same level of confidence onto this? And that's definitely not the case today. Okay, there's also alternatives to inflation, different mechanisms of trying to do this, and maybe those could still be true. Okay, at this point in time. So I just want to describe one observable that inflation predicts that would be very indicative. I mean, it's as close as proof comes, I would say, for this type of thing, because it's arguably the cleanest prediction that inflation makes. So I mentioned that inflation predicts fluctuations in the density because all the scalar field, the energy density of inflation is fluctuating. Okay? Of course, there's one fundamental field because it's a gravitational field, which is the graviton field. And that also must fluctuate, and so it produces a stochastic background of gravitational waves. It's the simplest prediction that inflation makes. There's no model dependence to it, except that the only parameter that dictates how large the signal is the energy scale at which inflation happened. So at this moment in time, actually, we don't know exactly at what energy inflation happened. It must, of course, happen at times that are larger than BBN to allow for BBN. It must also allow for energies larger than some plausible mechanism of baryogenesis. But other than that, it could be anywhere. In fact, we have some upper bound on the energy scale of inflation, which is 10 to the 16 GeV. But it could be anything up to from BBN scales to 10 to the 16 GeV. If we were to measure gravitational waves, we instantly would know at what energy scale inflation happened, because the amplitude of those gravitational waves depends only on that one number, namely the energy scale of inflation. Okay, so how can we look for those gravitational waves? So fortunately also is that these gravitational waves produce an extremely distinctive signature in the cosmic microwave background. So I haven't talked so much about this so far, but the microwave background doesn't just have fluctuations in its intensity, but the fluctuations themselves are also polarized. Because when a photon scatters off an electron, due to Thompson scattering, it produces polarized light. And there's a statistical distribution of that polarized light when we look at the cosmic microwave background. And so now, because polarization, of course, has direction, the polarization field can be decomposed into two different scalar modes. They're called E and B modes. Yeah? And the terminology is a little bit inspired by electromagnetism. That in electromagnetism, you also have the gradient of a scalar potential for the electric field, and then you have the curl of a vector potential for the magnetic field. Yeah? So there's a spherically symmetric mode that produces fluctuations around hot and cold spots that are where the polarization is arranged either radial or tangential. That's the E mode. And there's a second mode that creates a curl pattern, a swirling effect, which is what you're seeing in here in this simulation. Yeah. Actually, it's not just a simulation. This used to be a measured. So of course, some of you might have heard about this terrible episode where cosmologists thought they had actually seen this pattern, and this is the actual data at the time where they thought, by the BICEP experiment, where they thought they had seen this swirling pattern. Yeah, question.
Let me ask some questions related to gravitational waves. Let's imagine that again. We have two black holes, and they are rotating around each other, and they have in the ring down. They emit the gravitational wave, and we can detect it in the observational LIGO and Virgo. But how can you say that? Can you please explain the process of gravitational wave in the early universe?
Yes.
How is happening?
Okay, let me say a bit more about this. Yeah. So you're talking about kind of gravitational waves produced by black hole binary inspirals.
Yeah.
This happens in a late universe after a structure has formed. Okay, and these are nearby sources of gravitational waves. I'm now talking about gravitational waves that are produced out of the vacuum during inflation, 10 to the minus 32 seconds after the Big Bang. Okay? And now the question is, those gravitational waves are a stochastic background, just like the cosmic microwave background and the neutrino background that fill all of space. And the interesting thing is that those gravitational waves will affect the local conditions when a CMB photon last scatters off the free electron before recombination. And it's polarization that's being created then. So without those gravitational waves, that scattering, you can prove, can only produce spherically symmetric patterns around hot and cold spots. So it can only produce polarization that's either radial or tangential around hot and cold spots. In fact, if you go back to these stacked images that I showed in the last lecture, you can look at the polarization maps, and you see that they're only radial and tangential because we haven't seen a B mode. So this is purely coming from the E mode. But then the gravitational waves, of course, affects the space-time at the scattering event. And that then gets translated by the spin-2 nature of the gravitational field into this swirling pattern of the polarization. So the gravitational wave kind of fills all of space, and it affects the local conditions of the scattering, and therefore it affects the way the polarization pattern is being generated. Okay?
How can you say that this gravitational wave coming from the early universe?
How do you know it's coming from the early universe?
Yeah, this gravitational coming from the early universe. Can you?
Yeah, well, of course, it's some gravitational waves that was produced, at the very least, it had to be produced before recombination, because it affects things at the recombination, that's at the very least. But then also you actually create correlated signatures in the polarization across, again, distances that are super horizon. So these gravitational waves themselves also had to be produced, if you can see that signature, they also had to be produced before the hot Big Bang. And then so it's a consistent story to say that these things would be, both the density fluctuations and the gravitational waves were being produced by inflation. And it's very economical, by the way, because the two things that you have during inflation, independent of any model, is you have a density, a nearly constant density, and you have the metric. And those, if you just take fluctuations in the vacuum of those two things, the scalar density and the spin-2 metric tensor, then you create, first of all, the observed signatures and the intensity of the light, which is coming from the density. And then in the future, we might look for the second guaranteed signature of a spin-2 metric fluctuation. Okay. So you can have more signatures for inflation, but this is the minimum. Okay, this is the things that you have to see if inflation is correct at some level. Okay, and then so finally, just maybe 5 minutes left. So there's a number of ongoing experiments that are probing these. In fact, the future of CMB experiments is organized in stages. So we're currently at kind of stage 3 and actually transitioning into stage 3.5. And so there's really a number of experiments. So I've listed a few of them. They're usually they're at remote places. So they're at the South Pole or in Chile, in the Atacama Desert, just because the atmospheric conditions there are favorable for measuring microwaves. So that's ongoing. In fact, and then there are planned experiments. They were planned at the time when I made these slides 2 years ago. They're now actually kind of ongoing. So Simon's Observatory, for example, actually just started operation, and in the next year or two, you might actually see some announcements from this Simon's Observatory. It's using the facilities in the Atacama Desert in Chile. There's an upgrade, stage 4, the next generation of CMB experiments, which tries to combine experiments at the South Pole and in the Atacama Desert. Yeah, I should maybe have put that question mark on the South Pole, because just very recently there was some kind of uncertainty put on whether the South Pole facilities would be maintained by the US funding, and the answer at the moment seems to be no. So there was a bit of bad news for the stage 4 endeavor. But this might, again, politics might change. Yeah. And then finally, there's also a satellite experiment organized by Japanese researchers called Lightbird that will also soon that's already funded, and it will go into space at around 2028. Yeah? And all of these experiments are kind of optimized to measure these gravitational waves from inflation as one of their main kind of science target. Okay. So now, of course, we haven't seen it yet. We had one false alarm. If you were to see these B modes from inflation, or these B modes from the early universe, I think it would be kind of as close as we can get to prove that something like inflation happened. So then I think I would be confident to put this into this timeline of the history of the universe with much more confidence than we can do right now. And it would really complete kind of this story that I was telling about the history and the evolution of structure in the universe, from initial quantum fluctuations at early times that then became density fluctuations in the primordial plasma with sound waves imprinted in the CMB, and then the clustering of those fluctuations into galaxies and stars and the whole large-scale structure of the universe. Okay? So this finishes actually this lecture. I'm just going to conclude with 2 more slides for the entire course. Are there questions about this? Yeah.
Is there any hope of detecting directly the gravitational waves with LISA, Einstein telescope,
yes.
nanograv?
Very little.
Anything?
Very little. Yeah, this would also be amazing, of course, if we could measure the inflationary stochastic background, not indirectly by its effect on the CMB, but directly with some interferometer experiments. Yeah, there used to be, when I was a student still, and everything was like rosy, yeah, and like, anyway, long time ago, yeah, people were talking about things like the Big Bang Observer, BBO. You can read papers about what amazing things this Big Bang Observer could do. And that's a hypothetical experiment that works at the quantum limit of gravitational wave detection. Because at some point, the fundamental limit to detecting gravitational waves by measuring kind of distances between test masses, at some points becomes the Heisenberg uncertainty relationship of measuring positions in space. Okay? So that's kind of the ultimate. No matter how clever you are about technological advances, you will not beat Heisenberg, I'm imagining. And so literally there's an uncertainty relationship on the positions of the test masses that you're measuring. And so if you're allowing yourself to go to that point, you can predict the best that you can do. And even the best that you can do might not be good enough to measure. It depends on the amplitude but even for the largest amplitude of inflationary gravitational waves. And the reason is actually simple. Yeah? Why is it so hard to measure gravitational waves from inflation? It's because these gravitational waves were produced at very early times. And then, like any radiation, they redshift. So the amplitude of those gravitational waves decreased by 1 power of the scale factor. But the scale factor increased by an enormous amount from the time when they were produced until today. Okay? So we're just having, we stuck here on Earth just have to wait for too long for those gravitational waves to come to us, and they will decay in the process of traveling towards us. So that's why the CMB, these B modes are such an amazing trick, because they are capturing the gravitational waves at an earlier moment. It's like putting a detector at the time when the CMB was formed, and the gravitational waves have not yet decayed by that much. So they're still larger. So that's the trick we're exploiting. So here on Earth, we just have to wait too long. These gravitational waves will dilute like any radiation when it spreads out into space. But the CMB is one opportunity of catching these in the act earlier. Yeah. Okay. Any other? Okay, so let me just conclude, and then I can maybe open the floor for some general questions on anything. So just to summarize, I think we do have a remarkably consistent picture of the history of the universe, at least from microseconds after the Big Bang until today. So there's various events that we know with absolute confidence as just facts of nature. And I've listed them or drawn them up here. We also, I think, have tantalizing evidence for something that happened much, much earlier. There's rapid expansion that we call inflation, but we don't have proof, I would say, that this happened. And of course, maybe if we were to see these B modes, we would get proof of that early period. It's also important to emphasize that observations of the CMB in particular, I think, have really revolutionized cosmology. You don't have to go back so far to be at a time when the cosmological parameters were measured at order 1 accuracy. Yeah? For example, the Hubble constant that I was quoting at 68 plus or minus 2. And now we argue about Hubble tension between those values at the percent level. Yeah? But in history, if you go back just in history, Hubble's actual measurement of the Hubble constant was off by a factor of, I think, 10. Yeah? And this affects the age of the universe. So then the universe, with that measurement of the Hubble constant, was younger than the oldest stars in the universe, and so it made no sense. Yeah? So there was incredible uncertainty in measuring these things, and so the fact that we can even argue about something at the percent level and call this attention is amazing progress. And in particular, we have a model that describes all of this with just 5 or maybe 6 parameters. However, as I also highlighted, none of these parameters is perfectly understood. They all involve some kind of beyond the standard model physics, I would claim. And so there's many fundamental questions that we still have. So what is the dark matter? What is dark energy? Did inflation really happen? And if it happened, what exactly was driving this expansion? And then also I mentioned what is the origin of the matter-antimatter asymmetry. Yeah. So of course, I think there's a quote by Weinberg that says, like, physics thrives in crisis, and so I wouldn't call these things crises, but they're puzzles, and of course it's amazing when you have these puzzles to kind of try and get theory and observations to come together to explain these things. So thank you very much for your attention. Okay.
Thanks a lot, and maybe you can do it yours. Let's start over there, no?
Thank you. Yesterday you mentioned that there's a structure, yesterday, whatever. You mentioned that there's a structure of the light that we see in the universe as well.
Yes.
Can you look at this and then essentially get a projection of this light on the CMB, or is it more complex, or how do these relate?
Sorry, what did I say?
That there's like if you look at the light that we see in the universe, there's some structure to it.
I was probably referring to this first light, the cosmic microwave background. There's a pattern in these fluctuations.
Okay, so the actual density of matter in the universe, we don't see that much of a structure.
There's something called gravitational lensing. So you can actually, so as the CMB photons travel through the universe, they get ever so slightly deflected by the intervening large-scale structure. So if there's a large cluster of mass in front of the CMB light, then it will be bent, slightly. And statistically, it's not strong lensing in the sense that sometimes we have a galaxy being lensed around another galaxy and we see really arcs, multiple images of the background galaxy. It's not like that. But statistically, kind of basically the spots in the CME get deformed. Yeah? And so if they were perfectly spherical, by gravitational lensing, they would be squashed and rotated. Okay? And statistically, although the CMB fluctuations are not spherical, this effect of squashing and twisting of the fluctuations can be seen statistically, and you can measure, and in that way, you can measure all of the matter between us and the CMB. Okay, and then in fact, there's an amazing map that shows you where all the dark matter is integrated along the line of sight between us and the surface of last scattering. So we literally have a map using this gravitational lensing that shows us where all the dark matter lies.
And then does this have a structure, like also a power spectrum?
Yeah, indeed,
okay.
Of course. Yeah, just because, and the structure must be consistent, of course, with the measured 2-point function of the galaxies, because the galaxies will preferentially form in places with a lot of dark matter. Okay, so there's 2 ways of measuring this matter power spectrum, which is one is just by looking directly at the galaxies and measuring their 2-point correlations. But there's a second way of indirectly by measuring this lensing of the CMB, and that depends on how the matter is distributed. And so it depends on the same power spectrum, so you have 2 independent measurements of the same quantity. Yeah. Yes?
I just wanted to ask, when you take the Carroll limit in GR, can we still assume like the universe is homogeneous and isotropic? And also, can we say it's a fluid?
Okay, 2 things. So, sorry, can you repeat the first one? When I take what limit of GR?
The Carroll limit, when the speed of light approaches 0.
The Carroll limit. Oh, now I understand. Okay. Yeah, that's interesting. I mean, so taking some Carroll limit of speed of light going to 0. Do you do 0 or infinity when you do speed of light to 0? Okay. No, because there have been this is something the opposite. If you do the opposite of the Carroll limit of having some theory where the speed of light somehow becomes infinite, it's a drastic modification of special relativity, especially because, then you could maybe avoid the horizon problem. Because the horizon problem is related to the fact that light travels at a finite speed. If somehow in the early universe light traveled at a larger speed, then that could in principle allow for a larger horizon and then maybe causally connected. So these are kind of called varying speed of light theories. They were fashionable, I think, maybe like 40 years ago or something like that. Maybe this was even pre-inflation. And I don't know about the Carroll limit. It's okay. Maybe we can talk about it afterwards. I have some things to say about it, but not in public.
Okay. I think there's a question over there. Maybe you first.
Yeah. Okay. You want to go first?
Yeah.
Okay. So when we were talking about that the nearly constant inflationary vacuum energy was scale invariant, how is this possible if we are saying also that the densities are fluctuating? How can they correlate?
Oh, okay, good. Well, because so what we're talking about when we talk about scale invariance is the 2-point correlations between the density fluctuations. So how correlated they are across space, and that can be statistically still scale invariant. Although you, of course, in a given realization, you will have a fluctuation here and you will have a fluctuation here. All I'm saying is that on average, the amount of power in fluctuations separated by a certain distance is independent of distance. That's what we mean by scale invariance.
Okay, thank you.
So it's the 2-point function, not the 1-point function.
Okay,
I think
thanks.
now it's you.
Yeah.
So for the neutrinos, we would expect a similar background than for the cosmic microwave background, right? So would we see the same shape of the power spectrum, or does something change because neutrinos decouple before the photons?
Yes. Actually, this is a fascinating question. Let me ask this as a quiz to everybody. Okay? So the neutrinos decoupled 1 second after the Big Bang, so very early. Photons decoupled 370,000 years after the Big Bang. So the 300,000 years after the Big Bang creates a surface of last scattering. There's also a surface of last scattering of the neutrinos. Is that surface of last scattering closer or further away from us than the CMB surface of last scattering? Just by a raise of hand. Who thinks it's closer than the CMB? Who thinks it's further than the CMB? First. Okay. And then the rest thinks it's closer. So most of you think it's closer. Why? If it decouples earlier, it naturally should be further away. No? Because at more time, there's shells surrounding us at certain distances. Yeah?
The neutrinos have mass?
Exactly. It has to do with that. So there's actually a paper that I think Scott Doddleson wrote with somebody like you guys. And he was giving lectures, and a student asked this, and then they decided to figure this out and wrote a paper. You can find it on the archive by Scott Doddleson and a student, where they actually calculate this, and somewhat surprisingly, maybe because it's totally counterintuitive, the surface of last scattering for the neutrinos is closer to us. They decoupled earlier, of course, but then at some point they travel slower than the photons, and so they don't make it as far. And so the surface of last scattering of the neutrinos around us is actually closer, by quite a bit. So, okay, I forgot what the question was, but I think that was the answer. Sorry, but you asked, whether we can also see this neutrino background? Or?
Yeah, do we see like a similar structure in the power spectrum than for the CMB? Or is it different because of...
Well, we haven't, so that's the next level. So, you know, the CMB also went through stages. At first, so Penzias and Wilson by accident discovered the average temperature around them, yeah, with no fluctuations. So they found 2.7 degrees across the sky and perfectly homogeneous. And then ever since, people tried to measure things with more and more accuracy. And in fact, at the very last moment, in fact, there was almost a crisis point where, because people didn't know exactly, was the fluctuations 10 to the minus 3, 10 to the minus 4, 10 to the minus 2, okay? And so they were ruling out 10 to the minus 2 first, 10 to the minus 3 first. 10 to the minus 4 is really the last place where there's enough fluctuations for things to grow fast enough to explain galaxies. And so at the very last, but it could have been larger. It could have been 10 to the minus 3, and we could have seen it earlier. So there was a moment where we didn't see the fluctuations, and then Kobe saw them for the first time in the 1980s at the 10 to the minus 4 level, okay? The reason I'm giving this historical background is that for the cosmic neutrino background, we haven't even seen the average, okay? So the first step really would be to see that we have seen the average as an imprint indirectly on the cosmic microwave background, but we haven't seen it directly. There's very futuristic experiments called Ptolemy. There's an experiment called Ptolemy, organized by people at Princeton and elsewhere, where they look at inverse beta decay to measure the absorption of these neutrinos coming from the very early universe and study this capture. Yeah? The problem with those experiments is you need a lot of radioactive material, and it's hard, basically like you need nuclear amounts of these radioactive materials, and it's hard to not arouse suspicion of like hoarding weapon-grade nuclear material in order to perform this experiment. So that's actually just a practical problem of having a large enough amount of these things to study this capture. But that's something where in principle, you know, the back of the envelope calculations tell you could maybe in the future measure this directly. But at first, you would really just measure the average, because you have to average over the entire sky to get enough sensitivity. And then you can ask yourself, what's the power spectrum of these cosmic neutrino backgrounds? And I bet somebody has written a paper about this. It's an easy calculation you can do. Yeah. It wouldn't look, my guess would be actually just on the top of my head that it wouldn't look like the CMB. Because the CMB, the reason it looks like that is because photons and baryons are coupled, and there's photon pressure that does this. While neutrinos, the neutrino coupling to the primordial plasma is different. So one has to kind of take into account the different couplings between neutrinos and the plasma and the photons in the plasma and work it all out. I'm sure it has been done. Yeah.
So what happens to like energy densities during and after inflation? Shouldn't there be like some kind of reheating to make sure that not everything is too cold because your universe expands so much?
Yes. So there's an extra phase where kind of this inflationary energy gets converted into degrees of freedom of the Standard Model. And then these degrees of freedom, you know, they're relativistic at those times. This is before the electroweak phase transition. Everything is massless. And then by strong couplings, due to electromagnetism, basically, things come into thermal equilibrium. And there's questions about the efficiency of this process, and that depends on what couplings you assume. We don't know exactly how the inflaton, whatever it is, how it couples to the Standard Model, and that will affect how quickly this process happens and so forth. So there's a whole industry called reheating, where people calculate with different model-dependent couplings this process, how quickly this happens, which process, you know, how the things get populated and so forth.
Yeah, you can have one more question.
So Professor Tong mentioned that we have theories of quantum gravity, but they break down at certain energy scales.
Yeah.
But you mentioned that there is some graviton fluctuations going on in the inflation that makes these gravitational waves. Does that mean that this theory holds throughout all the energy scales that we see during inflation?
Yes. So what he, I bet, was referring to was kind of the Planck scale. Yeah. And so we know that inflation had to happen at energy scales smaller than the Planck scale. In fact, the size of the gravitational wave power spectrum that we probe with B-modes is predicted by the ratio of the expansion rate during inflation to the Planck scale, okay, squared. So it's a dimensionless number, and so because we haven't seen so if the expansion rate during inflation was the Planck scale, it would overproduce gravitational waves by an enormous amount, because the theory would be kind of strongly coupled gravity and There will be lots of gravitational waves, and we haven't seen that. Okay? So we definitely know that inflation, it's actually from those measurements that we know that the energy scale of inflation was at most 10 to the 15, 16 GeV, and the Planck scale is 10 to the 18-ish GeV. So at least 2 orders or 3 orders of magnitude below the Planck scale is where inflation happened. And that's why we actually have predictive power. We can compute in the effective theory of gravity. So we don't need full quantum gravity. We still use quantum fluctuations in a classical fixed gravitational background. Yeah? So that's something you can do. I mean, when people say we need, quantum mechanics and gravity don't like to talk to each other and they're totally inconsistent, that's partly true at the Planck scale, but at low energies it's totally fine. You can compute the effect of the classical gravitational field on the quantum fluctuations, and that's what we're doing when we're predicting signatures of inflation. There's a classical background given by the inflaton vacuum energy density, and then there's fluctuations on top of that, and you can quantize them as you always do.
All the way in the back. Yeah.
How or why can the universe expand faster than the speed of light?
Yes. Well, if you very carefully look at the law of relativity, it's a legalistic question, then it doesn't forbid this. So relativity just says that things can't travel through space faster than light, but space itself can separate faster than the speed of light. Okay? You can't communicate information in this way, but you can take pre-existing information and kind of stretch it to those large distances. Yeah. So it's just a fact of special and general relativity that this is possible, and in fact you always have that when the energy density is dominated by vacuum, constant vacuum energy density. All right. Sorry, maybe he hasn't had a chance first. Maybe do him first and then you.
So these density fluctuations happened in the early universe. Are these still happening today?
You mean the vacuum, the quantum fluctuations?
Yeah.
Yeah, as I said, they're happening here if you look closely. Okay. It's just right now space is not expanding at an enormous rate, at least on these scales here. Yeah. So actually now the accelerated expansion is not taking these vacuum fluctuations and make them classical. So I'm joking a little bit. I mean, yeah, vacuum fluctuations are happening either much more dramatically in kind of particle collider experiments, but also just in flat space. But you really need the combination of fluctuations of the vacuum and the expansion of space that takes these fluctuations separates them to large distances. And that separation has two effects. First of all, it creates this apparently acausal feature, and it amplifies the fluctuations because inflation has this switch from when things inflate and when things don't inflate, and that amplifies things. Yeah. So
how about in the outer space, since it's primarily vacuum, can structures still form due to these quantum fluctuations?
No, so as I said, these vacuum fluctations, they're there and they affect tiny things like the Lamb shift in atoms and the running of coupling constants at particle colliders. But basically what inflation does is it takes a quantum mechanical microscopic effect and it makes it macroscopic relevant for objects as large as galaxies and large number of particles. While when we do experiments in flat space now without this enormous expansion of space, the fluctuations are microscopic and they stay microscopic, and we only measure the effect is only on microscopic scales, not on macroscopic scales. So you need this stretching.
Yeah, we still have time. Yeah.
In the beginning, we said that the universe is the homogeneous and is isotropic, and we learned everything like formation of particles, atoms, and galaxies in the FRW cosmology.
Yeah.
In the inflation, we set the question: why is the universe homogeneous and isotropic? Why we didn't do in the beginning of the theory?
Okay. Yeah. Let me repeat it and maybe reformulate it as I understand the question. Okay. So I think maybe you're asking about the initial conditions of inflation. So inflation, indeed, and I didn't emphasize this maybe enough, it is a mechanism to take something that's actually wildly fluctuating. So it's anisotropic, it can have spatial curvature locally, and not homogeneous, it can have large fluctuations at different but it expands this by such an enormous amount that things get smoothed out. Yeah, it's a bit, if you take like a wrinkled balloon, if you just zoom, I mean, another way of thinking about it is that inflation is zooming in into a very small region of space, and as you zoom in more and more, even something that's widely fluctuating becomes smooth at short enough distances. And then inflation takes this thing that's smooth and homogeneous and isotropic and blows it up into the size of the entire observable universe. So it is indeed, it's a mechanism of taking kind of more generic initial conditions where you don't have to assume homogeneous and isotropic and making it homogeneous and isotropic. Yeah.
Why are we always like taking models with homogeneous and isotropic stuff? If when, for example, we have a constant background energy, but we also saw that energy can decrease with R. So is it because we have like some sort of patterns as explained before, or why?
Sorry, can you repeat? I didn't follow.
So I was wondering why our like cosmology models always take a homogeneous and isotropic space. If we have indeed a constant background energy, for example, but at the same time we know that energy can decrease with R and stuff like that.
Yes.
So why is it like that?
No, but actually, two different things. So first of all, the reason we take homogeneous and isotropic is twofold. One, observationally, we see when we look out in the sky and we statistically measure all the distribution of galaxies and the cosmic microwave background, it shows us that it's approximately homogeneous and isotropic. So it's self-consistent. Then on top of that, you could ask why. I mean, it's an observational fact that this is a good approximation on average to our universe. But then you could ask why, and then I just explained that inflation actually is a dynamical mechanism that makes things homogeneous and isotropic. And then I think you had one confusion where you said these energy densities are decreasing, diluting, but they're diluting homogeneously. So the radiation, the matter, and the dark energy, it was only a function of time. It was never a function of space. So at that part in the lectures, we only were talking about the homogeneous densities, and they dilute, but they dilute everywhere in the same way across the entire universe. So there's no inhomogeneity.
We're a bit over it. Is it a short question? I think we missed you before, right? So short question, please. And then we finish.
Okay, if space expands faster than light, are there places where we have space expansion where we can expect gravitons and gravity not to exist?
Oh, sorry, can you repeat it? I didn't hear it correctly.
So you said that space, we have places where space has expanded faster than the speed of light.
Yeah.
And graviton being a particle, can we expect these places where light hasn't reached yet, to be like spaces where gravity doesn't act or exist?
Okay, maybe you can come. I still don't quite get the question. Maybe you can come down.
If a graviton goes faster than light, if space expands faster than light, was that the question? Yeah. So gravitons, they.
Yes.
But it's.
Yeah. Oh, good. Yeah, I think it's true. So imagine space as a grid of points, yeah, and a graviton is sitting on a grid of that point. If space is not expanding, the graviton would kind of move across the grid of point, and it would, different coordinate points will be crossed by the graviton. When we say space is expanding, actually nothing is, let's first do a stationary particle that's not the graviton, just us sitting here. We're sitting on a grid point on this hypothetical grid, and as the universe is expanding, we stay on that grid point. It's just things are separated away from us. And so the graviton itself is moving through this space, satisfying the speed of light constraint, but space itself is expanding, and so it's a bit of an illusion where relative to a fixed observer, it appears like the graviton is moving faster than the speed of light, but it's not moving through space at faster than the speed of light because you have to take out the expansion of space itself when you make that judgment. So relative to the grid points that are labeled on the space, which are just separating from each other, there's no faster than the speed of light.
That's also a good point to end, and thank